thanks again for inviting me and giving this opportunity to present our paper. So today I'll be going through the few short adaptation for OpenSea detection models. I just tweaked this title a bit. It's actually Grounding-DINO, adapting Grounding-DINO for agricultural tasks. The reason why I kind of changed this is because of its broad applicability across domains and also not just confined to Grounding-DINO. So again, to introduce myself, I'm Sudhir Sornapudi. I'm a senior data scientist and also lead a team advanced vision intelligence at Corteva Agriscience within data science R&D. You people will be wondering, what is Corteva? We are a corporate company and we sell seeds and chemicals for the agriculture. So that for that exact reason, I had a 1.5 minute video. So I'll just start with that to let you know who are we. Let me know if this is coming through well.
Who was the first farmer? Who planted a seed and grew our world? It was the birth of progress. Because someone could grow a little corn, some wheat, rice, humanity could grow everything else. This is the power of farming. The power to grow our civilization. But who could have predicted how big civilization could get? Our population is increasing. Our natural resources are declining, and our planet's climate is changing. So farming needs to change too. And it has, with smarter tools, sustainable practices, and ever higher yields. Farming gives progress to the world, and the world is giving it back to farming. We're Corteva Agriscience, and we're here to support the people who support us all. With stronger seeds, precise crop protection, and data you can count on, we're bringing the next generation of farming to the next generation of farmers.
Hopefully that got through well. So can I go ahead? Is
Yep.
that, am I audible? Okay. So yeah, as you have seen, you might be wondering what is an agricultural company doing here? Do they do computer vision? But in fact, we do a lot of computer vision, and it ranges from cell level to space, cell to space. That's how we call it. It's because it's a lot of research that happens for hybrid seeds breeding at a genetic level, and you look at genes and cellular level nuclei, the phenotype of that, and then also the plant, how they grow, how much yield do they bring in. So we have lab greenhouses experiments happening, and we always capture images. And for high throughputs, we image, and instead of doing it manually, we can automate a lot of processes with this computer vision techniques. So as drones, we also fly drones in the fields so that we can estimate how healthy the fields are or if there is any stress, and also count in all the environmental factors, even remote sensing data, so coming from satellite. So it's pretty broad, and that is why I would like to highlight why agriculture is challenging for computer vision. As I just mentioned earlier, it's so diverse, and diversity being it's not just diverse, it's also very complex because it's coming from nature, and as all biological activities, it keeps changing, and there are so many factors that influence the behavior of whatever the problem you're tackling. So it's out of our hands. That there are so many things that you can control, but you still want to automate the process with computer vision. So that's why it's very complex. And there is also very high inter-class variability is obvious, but also within classes, there is also very high level of variability. And again, if you see some from fields as plants, when they are baby plants, it's pretty, they are, when they are planted side by side, they look separated, but as they grow, they start occluding themselves. And there's a lot of clutter from background and weeds. So obviously, when we go ahead with this real world applications, we need to rely on supervised learning, and manual annotation is always very labor intensity or very costly. So we look for unsupervised, self-supervised techniques or leveraging foundation models. So that's what this paper is about. And again, the idea is how to scale up and adapt these AI solutions. So here, let me get a laser pointer. So again, open set detection models, as you're all aware, these are open, you can call it open world or open vocabulary. These are very powerful models, and they can detect any kind of an object beyond fixed categories. So usually what you have seen from ImageNet is you always have like thousands of classes, and you can only predict a class within that fixed set of classes that they have given. But open set models are very powerful, that with simple textual input, you can detect anything in an image. But this kind of model works really well with internet data, because that is what it was trained with, but does not really go well with agricultural or medical images or any domain specific niche needs. So that is the challenge of OpenSet. Again, the zero shot application is like you just give in any kind of an uh, text based prompt, and you want to identify that is the limitation. So there is a big gap there. So what we used here is Grounding-DINO, which is built on top of Dieter style transformer detector. So the image, as you can see, we feed an image. There is an image encoder here. So that's based on SwinB, and this text backbone for dinos is with BERT text background. Uh, and you get this text embeddings and image and embeddings, and there is this feature enhancer layer, which kind of uses some self-attention and cross-attention to make those features what do you call communicate with each other, so that they get it's like you get features that are text aware image features, and the text embeddings are image aware. So those you get much more powerful features, and then these are fed to language guided query selection, so that when it's a query selection, we want to identify these bounding boxes, and from pool of boxes, right? What are those the boxes that are really of our interest? So that is guided by this text, and ultimately with this cross modality decoder, you do some contrastive learning here and then map this what do you call text embeddings with these image features, and then get a mapping. And that's how this Dino was designed. But again, what's wrong with this zero shot prompting? Because it's very, as I said earlier, there is a lot of occlusion overlapping. And imagine crop weed. When I say crop to the Grounding-DINO model and a weed, both are plants. So crop is actually your cash crop, whatever the crop of interest you're growing, and weeds are any other crop. Or say when you do cycling, if you have seeds from older plantation that grow up again, so cornfield, there's a soy plant that's growing up, it's a weed, it's still considered weed because that's not what you're uh, harvesting for. So you need to differentiate that, and how to differentiate is difficult for a zero shot model or open set model like Grounding-DINO. So it really fails in these real world conditions. And these are some of the examples that you can see. We are trying to identify plants here, and the differentiate between weeds and plants. Again, you can see it kind of detects all 3 or 4 plants at a time as a big block. And again, fruit detection. So we want to detect each individual fruits, but that's not the case. It draws boxes across, even peppers. So these are some of the examples. So what our solution is to use few shot adaptation. And the twist here is we are not using text encoder. So BERT model itself is It is a compute heavy module. So what we did is we took off that module completely and we randomly initialized uh, the text embeddings from here. So by learning these new text embeddings, these are only like few thousand parameters. Uh, so as few as like 4 or 8 images. So that's a few short images per class that we are using, and then we train the model with that. And when we have a powerful model. So as you can see with blue indicated, all of these blocks are frozen. So we are not changing anything. We pre-train we lowered the pre-trained weights of the grounding-DINO, but all we are doing is like we are initializing this embedding text embedding, and that is the only learning parameter here that we are trying to modify within this few number of epochs. And the model trains very quick. Within couple of minutes, you have a trained model, and you can see. I'll show you the results how well it comes up. Again, just a bit background on how few shot method actually work. So what we've done, as I said, is initialize that text embeddings randomly. And again, we make sure we are matching the BERT output dimensions. So it's basically n by 768 dimensions. That's what we figured out that the right dimension. And the number of tokens is like an empirically kind of chosen number. So we ended up choosing 4 tokens per class. So kind of to describe one class, we are choosing like four tokens for it for each class. And then as you can see, the bipartite matching is basically we are getting this from the data model that to what do you call find the matching between predicted and the ground truth objects. And the total loss, as you can see, is pretty much what do you call the focal loss for the classification, and L1 and then generalized IOU loss. These are for the bounding box regression losses. So in total, again, we got these lambda values. These are hyperparameters, and we ended up choosing 1, 5, and 2 respectively for lambda 1, lambda 2, and lambda 3. And we used Adam W optimizer to update these weights. So these weights are pretty much this text embedding weights, and with couple of iterations, not couple, almost like 50 to 100 iterations, we could get very good, powerful embedding. And this is the experimental setup. We kind of tested this model across 8 different data sets. So this is a sample of images that you can see of what we were used. And we also done this on the satellite image, which is Dior. The reason why we choose this data set for satellite imagery is because it has like very good journal publications and is an active research space for few shot. On remote sensing to detect the regions or the classes. And that is like exact reason why we choose this satellite imagery, and we actually surpass the state-of-the-art results there. And we also compared zero shot approach and few shot approach with compared both of them, and also YOLO baselines. And these were the MAP was the metrics we used for this. So when you compare with zero shot versus few shot was doing great job, just with few number of images, as few as, so we again, if you look into the paper, we have a lot of more numbers there. We tested with 2, 4, 8, and then increased it to 16. So you can see how as you increase the number of images, it was doing pretty good. And you can see the enhancement compared to zero shot. So that clearly indicates that there's a big gap if we just use grounding-DINO as is. And now with 4 shot and 16 shot images that you can see, these and you can compare with zero shot, the boxes are much better. So the detections are more accurate. So how does this compare with YOLO and SOTA? So what we did is we took YOLO version 11 model and trained the model just with those few number of images, because those are the set of images that are annotated. And when we train with YOLO V11 with those few number of images, it was lagging behind, and we were almost like we have a gain of 24% MAP. And it also output, as I said earlier, it outperforms the state-of-the-art methods on the remote sensing. So these are some of the earlier papers in the literature, and as you can see, this simple model leveraging the power of Grounding-DINO could surpass the state-of-the-art uh, models for detecting these objects. So as you can see, it's pretty much like identifying ships, chimney, or these are all satellite images. Uh, but the tweak here is like the 3-shot, 5-shot, the whatever shots that you see here. We set up a different experimental setup for this data set because we took what these papers have done earlier. So when I say 3-shot, it's 3 images per class. So that has this so 3 objects or instances per class. So that's what the 3-shot means here. Uh, Now, this is all good with object detection. Now, coming to instance segmentation, how does this do? It does really good. So what we did is we just added SAM to here. Whatever the bounding boxes, we got these predictions. We kind of use them as prompts to SAM2 model. And then now you can see this is a sugar beet image, and you can see very good leaf segmentations happening across these leaves. And then these are all we have done is training that modified Grounding-DINO with few images, and then Sam was giving these nice masks for each of these regions, which wasn't possible directly using Sam also. So the key insights and takeaways is zero-shot open vocabulary models, they struggle in any kind of domain-specific regions, especially in agriculture or medical, it really struggles. So few shot is a way, and leveraging these foundation models like that are well trained, they know really good representations of images of the vision. Uh, it just leverage them and then just making some tweak, modifying the text embedding, we got very effective results. And again, this kind of gives you very good efficiency in annotation. So all you can do is like you use this few shot approach. Now you just annotate 4 images, 5 images, train that model that we have, and say you have 1,000 or 10,000 of images, you can predict on it. So you are at a very good start point instead of doing directly from scratch. Imagine 80% of or 90% of your work is done, and you go and QC the rest of the annotation so that you have very good ground truths available for that model. And again, as I said, this approach generalizes very well across modalities. As I said earlier, with microscopic lab, with field, satellite, it does really good. And again, the model can be trained very, very quickly. So it's very easy to scale and adapt to all the AI solutions. So what's next? Finally, is we would like to explore more of the adaptation. So low rank adapters is something we want to try understand if we can use it, because we have frozen all of these vision encoder blocks. What if we can have these adapters and then fine tune it, which can make it much more powerful and make incremental improvements on this model that we have right now. And we can also integrate this same setup with YOLO World or YOLO E, any kind of open set model, detection model. We can integrate this setup. And again, ultimately automate the annotation for all the pipelines that we have in the domain. So with that, I'll close my presentation. Thanks for the opportunity, and I'm open for questions.